So okay, it's time. So it is my pleasure to have Christopher Felder from Washington University, who will talk about analogues of finite Blaschke products. So please.
Yeah, thank you. And first, I want to say thanks to the organizers. This has been really nice. Especially today, we've seen a lot of really interesting talks about how to think about inner functions, mostly from a complex analysis standpoint. I'd like to offer a little bit of a different taste of maybe describing or detecting or characterizing certain inner functions more from an operator theory standpoint. So I'm going to talk about analogues of finite Blaschke products. And these will be, from an operator theory standpoint, sort of the functions that play the roles of play the role of finite Blaschke products, but in other general reproducing kernel Hilbert spaces. Okay, so we've been seeing this all day. So we're going to take a finite Blaschke product. I'm going to let my zeros be beta j's. And this, of course, will be the unit circle. Okay, okay, so the degree 1 Blaschke product is called a Blaschke factor. We've seen that these are all automorphisms of the disk. We also know that any finite Blaschke product is an element of H2. And also that these are what we call inner functions. Okay, so the modulus of a Blaschke product is equal 1 almost everywhere on the unit circle. Okay, so I want to start with a very simple observation, but it's sort of the key observation for this talk. So I'm going to take a Blaschke, finite Blaschke product, and I want it to have simple zeros, none of which are 0. And I'm going to call these beta 1 through beta n. Okay. What I'm going to do is I'm going to apply just a partial fractions decomposition to B. Okay. And so what I get there, you can notice that the degree of the numerator is the same as the degree of the denominator. So I have to do some factoring. I get a constant out. And then I'll have a sum of things that look like Cj over 1 minus beta j bar z. Okay. All right. So the key thing here, though, is in H2, the reproducing kernel, referred to as the Zegel kernel, which I'll write as S lambda, is 1 over 1 minus lambda bar z. So what we see is that every finite Blaschke product can be written as a linear combination of reproducing kernels. Okay, where the first one will be the kernel at the origin, and the other kernels will just be the kernels at the zeros of the Blaschke product. Okay, so I want to generalize this idea. So I should tell you where. And so our setting will be this calligraphic H, which is just going to be a Hilbert space. I want complex valued functions on some planar domain. I'm not really, we don't have any hypotheses on connectedness or anything like this. We just want 0 to be contained in our domain. Okay. We do, though, want the following properties for H. We want to be comprised of analytic functions or holomorphic functions, and we want the polynomials to be dense. So I'll use this P here to denote the polynomials. Okay. And of course, we want the forward shift operator. So this is kind of where the operator theory comes in. We want this to be bounded on H, right? So this is just multiplication by your independent variable. Okay. And further, we want a reproducing kernel Hilbert space. Okay, so this means that point evaluation is a bounded linear functional for every point in our domain. Okay, and namely by the Riesz representation theorem, we have this, what we call a kernel function. Okay, so I'll denote this by KW. Okay, and so some of the spaces you can keep in mind are maybe Dirichlet type spaces. Okay, so if I take alpha to be an R, I can define D alpha to be, say, power series. So that this sum is finite. Okay, and this defines the norm on D alpha. So when alpha is 0, we get the Hardy space. When alpha is 1, we get the classical Dirichlet space. When alpha is -1, we get the Bergman space. Okay, so you can think about these if you want to keep a close example nearby of something that's not H2. Okay, so now I want to move to shift invariant subspaces. So if we have any function f in our Hilbert space H, since the shift is bounded, what we can consider is a subspace of this form. Okay, so this will be the shift invariant subspace generated by f. Okay, and really all it is just the polynomial multiples of f closed up in the topology on H, the norm topology. Okay, so let's make another quick little observation. And suppose we have some polynomial that will be in H by hypothesis on H. Okay, and we're going to take distinct zeros that are non-zeros for this polynomial. Okay. Well, really quickly, what we can see is that if I take PQ for any Q that's a polynomial, the kernel functions at the zeros of P will be orthogonal to PQ for any Q, right? Because this P beta I is just 0. Right? So K beta I is orthogonal to bracket P. That's just because PQ is going to be dense in bracket P. All right. But something stronger is actually true. That bracket P is precisely the span. It's the orthogonal complement of the span of the kernel functions. Okay. And you can prove this using some dimension counting arguments. So what we've done here really is we've taken sort of a shift invariant subspace generated by a polynomial, and we have associated it to some kernel functions. And so let's go back to finite Blaschke products and think about what happens in H2 here. Okay, so again, we're going to take our polynomial with distinct zeros, none of which are going to be 0. Then, if you recall, these are the Szego kernels. We have that bracket P is just the orthogonal complement of the span of the Szego kernels at the zeros of P. And so, well, we have that B of Z. We saw before that was a linear combination of Szego kernels, right? So this is going to be in bracket P. Okay, so our Blaschke product with the zeros of P. Oops, wrong tool there. The Blaschke product with the zeros of P will be in bracket P. Okay. All right. So what we want to show now, though, is that because we had this observation before, about when we did the partial fractions decomposition on B, what we can do is just take, subtract over this thing. This is all that I did here. And then we get the sum of these, this linear combination of kernels. This has to be in bracket P perp. Okay, so the point here is that now if I hit everything with just the orthogonal projection, so this is orthogonal projection onto bracket P, and I'm just applying that here. I think this is a typo, sorry about that. I think this T should be here. We just get that the projection of some constant times the kernel at 0 is our finite Blaschke product. Oops. Okay. And so there's something a little bit stronger that can be said, and it's that this is actually a characterization, right? So we can sort of detect the finite Blaschke product by sort of coming up with a polynomial and looking at the projection of the kernel at the origin onto the shift invariant subspace generated by that polynomial. Okay. And so some authors sort of so yeah, I mean, up to a harmless constant, this is going to be an inner function. Okay, and so this is just the theorem that I just said, and so yeah, so if you have f, if f is inner, and it's going to be a finite Blaschke product if and only if it's the projection onto a shift invariant subspace generated by a polynomial of the kernel at the origin. Okay. All right. So there's been a lot of recent study about generalized inner functions. Okay. And these are functions that satisfy the following. Okay. Excuse me. So we say f and h is h inner if f inner product z to the kf is 0 for all k greater than or equal to 1. Okay, and so I was started to get a little bit ahead of myself a second ago. Some authors also require that the norm of f is 1. I won't require that throughout this discussion. Okay, so what's equivalent to this definition is that this definition of inner is to ask that f is a constant multiple of the reproducing kernel at the origin for bracket f. And you can see this essentially just because if I take f pf and I take, and p is a polynomial, essentially just what I'm going to get is p of 0 bar times the norm of f squared, because all of the powers of z, non-zero powers of z, are going to die out. Okay. All right. Okay, so another fun fact is that this definition of inner coincides with inner on H2, right? So you could sort of see that just because if I look at, if I look at f z to the kf, I'm going to look at the integral maybe on the circle of f z to the kf bar, okay? And because f is inner, this is just going to be z to the bar k, and this will give me 0 for all k not equal to 1. Okay. All right. So this really is a generalization of an H2 inner function, a classical inner function from an operator theory standpoint. Okay. All right. So let's go back to our sort of general space H. Again, recall this is going to be some set of analytic functions on a complex domain omega that contains 0. And I want the polynomials dense, and I want the shift to be bounded. Okay, so the question is every H inner function that can be written as a linear combination of kernels, is this a projection of K0, so the kernel at the origin, onto a shift invariant subspace generated by a polynomial? Okay, i.e., is F equal to the orthogonal projection onto bracket P of K0D for some polynomial P. I guess I should really have a D here. And by this D, I mean K0D. This is going to reproduce sort of the Dth derivative. So F inner product K0D is going to be F to the D0. This corresponds to sort of when you have the case that if you think back to the Blaschke product, if the Blaschke product has a 0 of degree D at the origin, the replacement is instead, where is this at? The replacement here is that F to the D, the Dth derivative of F at the origin is non-zero. That's how that hops over. Okay, so this is sort of the main question that motivated this, and I guess I should have said that all of this is joint work with Triu Li at the University of Toledo, and this comes out of a paper that should be appearing in the bulletin of the London Math Society, and this is kind of the main question that we set out to answer. And the answer is yes. And what you get out of this is a characterization of functions. Okay, so here's the theorem. And so if we take any H inner function, suppose it has an order 0 of order D at the origin, okay, then it's going to be a linear combination of reproducing kernels if and only if F is a projection of K0D onto a shift invariant subspace generated by a polynomial. Okay, and so functions that arise in this way we say are analogues of finite Blaschke products. All right. So I suppose if you understand the sort of the orthogonal complement of shift invariant subspaces generated by polynomials, this isn't too crazy of a result, but there really is a surprising amount of work that goes into this when you want to do it in the generality that we've done it. Okay, so there's sort of this theory of reproducible points. So these are points that might not be in your domain, but that's point evaluation is bounded at that point still, and lots of sort of polynomial trickery. Okay. And so what I want to end with is sort of answering what it's good for. Okay, so what we were able to show in this paper is that all rational Bergman inner functions, okay, so functions in the Bergman space that are rational and satisfy, say, f z to the k f is going to be delta k0, that these all are analogues of finite Blaschke products, meaning that you can actually write them as a linear combination of reproducing kernels. We also extended some work of Sego and Kobos about there being no entire inner functions in weighted Hardy spaces except monomials. Okay. Excuse me. And a handful of other things that we would like to get around to, namely, what sort of results can you translate from H2 into other spaces using the analogues, the replacements of the finite Blaschke products. Okay. All right, so I will end there. Thank you.
Okay, so thank you, Christopher, for this beautiful talk. So, is there any question or comment for Christopher?
Chris?
Yes.
Very nice talk. The kernel you use the Jigo-Cauchy kernel, yeah?
Yes.
Did you try your methods for other kernels, like, I mean, even classical kernels in, say, Dirichlet space, or, I mean, other known spaces? I mean, these are for Hardy spaces. What about other kernels? Did you try to see what it gives us?
I suppose not, but all of the framework is there so that it should work. You should be able to write down what you want. It's just, it turns out that you don't have a nice description like you do in H2. You can't sort of, you can't have a general formula like you do for say, if you want to move from degree n to degree n+1, sort of in the analog of the finite Blaschke product. There's not a nice description to do that, and essentially it's because the norms aren't nearly as nice. You have to satisfy all of these orthogonality conditions, and so your constants become sort of ugly.
Thank you.
Yep.
Is there any other question? So, if not, let's thank Christopher once again.
Thank you.